Hello, everyone. So, this is the first lesson. We are on a new chapter. So, we're going to start with the very first one, which is about exponential growth and decay functions. Okay. So, let's define what an exponential function is. Okay. So, an exponential function has the form y equals b raised to the x. Okay. So, where a is not equal to 0 and b is a base, which is a positive real number other than 1. Okay. So there are cases. So again, there are two types depending upon what A and B is. So if A is positive and B is positive greater than 1, okay, then we have what you call an exponential growth and B to be the growth factor. While if A is positive and B is a fraction between 0 and 1, then what you have is an exponential decay where B is the decay factor. Okay? So notice these are the parent functions. Okay, so parent functions for exponential growth. So notice that this one is growing up. Okay, so again, b here is greater than 1. Okay, so x-axis is the asymptote. Notice it goes down, it doesn't touch the axis. Okay, and then it goes up increasingly fast. Okay, domain is all real numbers and the range is all positive numbers. Okay. And that also goes to the fact for exponential decay. So the graph goes down as x gets bigger and bigger. So it's kind of like decreasing. Okay. So again, still x-axis is the asymptote, and the domain is all real numbers for x, and the range is all positive numbers. Okay. So let's now try to graph. Okay. So when you graph, we start off with a table. Okay. So like say if I have one to graph y equals 2 raised to the x, I'm going to start a table of values. So I have now here -2, -1, 0, 1, 2, 3, and then I get the y values by just simply plugging in the x values to the equation. Okay? And then once I have that, I'm going to plot them into the coordinate plane, and this is what I'm going to get. Okay? So notice this is the graph of y equals 2 to the x. Okay? So you can also do this in Desmos if you can do desmos.com, and then you can just simply type in the equation. It's going to look like this too as well. Okay. So this is an example of an exponential decay because the base is a fraction between 0 and 1. So if I plug them in, a table of values, okay, so the values of y can be obtained by simply plugging the x values up here, and then plot them off, then you get the equation. So you notice it goes down, okay, from here to here. So again, you can still do that on Desmos too as well, okay. Now we have what you call exponential models. Since we have growth and decay, so we have a growth model, and then we have what you call a decay model, okay. So the ones marked in red basically are the growth rates, okay, and the decay rates, okay, or the decay factor, okay. So R basically is the percentage of how is it going up and the percentage of how is it going down, okay. Now one specific example, okay, of exponential growth and decay is the spread of the virus, okay. So you know already, but we are already on a pandemic, okay. So knowing a bit of math to help us understand how this really virus spreads out is important. Okay. So notice this was just like months ago, but now it's all over the world. Okay. So generally, a typical virus typically spread exponentially at first if there's no immunization available. Each person can infect multiple new people. Okay. The coronavirus that is affecting China, it can be devastating. The coronavirus already reached the US as a result. So if we know the rate at which they typically spread is important when you're trying to contain and treat an outbreak. Okay. So let's say, for example, So you're working in an international aid organization, and there are simultaneous outbreaks. Okay, and there are two types of coronavirus: coronavirus A1, coronavirus A2. Okay, so your organization has only enough resources to travel and to help in one location. Okay, so do you rush to help the coronavirus A1 infected community or the coronavirus A2? Okay, so once you know to do where to go, you need to have information. Okay, so like say for example, let's go on to this one. Suppose there have been 30 cases of reported coronavirus A1 outbreak, and so far it has an infection rate of 4% per day. The deadlier coronavirus A2 has only been reported one person and has an infection rate of 11%. How many people will be infected with each other after 15 days? Okay, so it's important to you have the information to determine which exactly where you want to go. Okay, so first you have 30 cases for A1. Okay, and it's going at a rate of 4% per day. However, coronavirus A2 has one person started and then an infection rate of 11%. Now the question also, we have 15 days incubation. Okay, how many people will be infected after 15 days? Okay, so we're going to use the math that we have in order to solve this equation. Okay, so we use the formula again, since this is a spread, so it's exponential growth. So y equals a plus 1 plus the quantity 1 plus r raised to the t. Okay, so coronavirus A1, it has 30 cases with a going rate of 4% or 0.04, and then the time is 15. Okay, so if I do that, substitute the value, so it's going to be 30 times 1.04 raised to the 15. By 15 days, I have about 54 people. While coronavirus A2, it started with one person. However, the infection rate is 11% or 0.11. Then t is 15. So again, you just have to substitute. Okay, so y equals 1 plus 1 plus 0.11 raised to the 15, or 1 times 1.11 raised to the 15. Y would be 4.78, or approximately 5 people. So basically from the 15, after 15 days, I would probably go here, but I have to wait because we don't know how this one spreads. Okay. Again, one thing to consider out before jumping on a plane, though, if the infection rate peaks at 60 and then fizzles out. Okay, how many people will be infected at the peak in each community? So basically, you're just simply changing t to 60. Okay, so I'm gonna leave you to that, solve that, and then you decide. Okay. So there are many also other applications of exponential growth and decay. One is car depreciation. Okay, so again, remember when you buy a brand new car, as soon as it leaves the dealership, the car value depreciates. So this one, the value of the car decreases. So it's going to be kind of like an exponential decay. Okay, so the value of a car, Y in thousands of dollars, can be approximated by the model 25 times 0.85 raised to the t, where t is the number of years since the car was new. Okay, so let's tell whether the model represents exponential growth or decay. So this is obviously, okay, a decay. So since the base is 0.85, okay. Now identify the annual percent increase or decrease in the value of the car. Since this is a decay, so it's automatically a decrease. So the decrease based from the following formula would now be 1 minus whatever the percent should be equal to 85. And that percent would be 0.15. Okay, or simply the percent decrease per year is like 15%. So the value of the car decreases 15% every year. Okay, another one would be world population. Okay, so in 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Okay, let's write an exponential growth model giving the population in billion t years after 2000. And then we're going to estimate the world population in 2005. Okay, so notice it started with 6.09 and increasing by 1.18%. Okay, so 1.18% would now be 6.09 and R would be 0.0118. Since this is growth, again, use the formula 1 plus R. So that's going to be Y equals 6.09 times 1.0118 raised to the T. So if I want to choose the population at 2005, that's going to be 5 years after 2000. So it's going to be about 6.46 billion. So you got to use a calculator for this one, okay? Now, chemical radiation, another one, okay? So the amount Y in grams of the radioactive isotope chromium-51 remaining after T days is given by the formula Y equals A times 0.5 raised to the T over 28, where A is the initial amount in grams, okay? What percent of the chromium-51 decays each day? Just simply write the original function first, okay? Now you need to express this in terms of T, right? So I have to move 28 in and then simplify this one, okay, which is 0.9755, and then subtract that from 1, you get now the percentage, okay? So it's about 2.45%, okay? So one last one, which is basically what most of you use and you're going to experience, is compound interest. So this is the formula when it's for compound interest. So suppose you have a money deposited in an account in a bank that pays an interest, okay, and compounded n times a year, okay. So your money after t years is given by this formula, okay. So when it's the rate, okay, so number of times n depends on how many times per year. If it's 1 time per year, we call it compounded annually. If it's twice a year, it's going to be semi-annually. If it's every 3 months, it's going to be quarterly. Okay? If it's going to be every month, that's going to be monthly. Or sometimes it's been compounded daily. Okay? So let's have an example. Suppose you deposited 9,000 in an account that pays 1.46% annual interest. Find the balance after 3 years when the interest is compounded quarterly. So let's have what we have here. You have an initial money, which is 9,000. The rate or interest, okay, is 1.46 annually, okay, but it's going to be compounded quarterly, and then find the balance after 3 years. So let's have now the following. So principal money is 9,000, R is 1.46%, okay, N is, you're going to be quarterly, so N equals 4, and then T is 3 years. So all we got to do is just simply plug this all into the formula right here. Okay, so I'm substituting P for 9,000. R over N, it's 0.0146 over 4 times 4 times 3. Okay, and then again, now if I substitute and use a calculator for that, I get the money to be approximately equal to $9,402.21. So after 3 years, your money had an interest of about $402.21 from 9,000. Okay? So if you don't have any questions, okay, I'm gonna assign work in Big Ideas for this, okay?